All right, let's go ahead and get started with podcast number 3, dealing with the mole, which is finally the introduction to the mole. Now that you have some of that background information of how scientists led up to this idea of the mole, you're good with sig figs, you're not going to make any mistakes putting numbers in your calculator. So now we're finally ready to get into it. So I'll begin with a question. What mass of oxygen has the same number of atoms as 1 gram of hydrogen? All right, and we've already talked about this. If we look at the relative atomic mass, so if you look on your periodic table, you'll see oxygen is about 16 atomic mass units, or exactly rather, and therefore it weighs 16 times as much as a single hydrogen atom, which weighs on your periodic table 1.008 atomic mass units. Okay, so we're going to look at this 16-to-1 ratio here. So it requires 16 grams of oxygen to have the same number of atoms as 1 gram of hydrogen. Now, I've tried to give you some intuition. We did the whole paperclip thumbtacks and all that, so hopefully that makes sense to you. All right, and so the idea is, well, we can extend this reasoning to all elements. So, for example, iron, 55.85 grams of iron is going to have the same number of atoms as 1 gram of oxygen, 1 gram of hydrogen, as 16 grams of oxygen, as 35.45 grams of chlorine, as 22.99 grams of sodium, and so on. They will all have the same number of atoms. Okay, so let's get a definition for the mole here. A quantity equal to the number of atoms in the atomic mass of any element expressed in grams. We've already gone through examples, but for example, lithium, 6.94 grams. All right, so that's going to have the same number of atoms as 9.01 grams of beryllium. All right, and the amount of that substance containing the same number of chemical units exactly as 12.00 grams of carbon-12. Now, again, from the last podcast, I gave you a little bit of idea behind the unified atomic mass units, the physicists, the chemists coming to an agreement on using an isotope of carbon, carbon-12, as the standard. And so that's what's been used, okay? This is leading up to a very famous number, and I bet many of my students are familiar with his name. In my class, we will refer to him as his full name of Lorenzo Romano Amadeo Carlo Avogadro. Okay? Now, his number is the number of chemical units. Okay, so when we say chemical units, we're talking about atoms, molecules, ions, electrons, particles, photons. All right, so that's what we're referring to. And that's the number of chemical units in a mole. And that number we will express with 4 significant figures in this course as 6.022 times 10 to the 23rd. That is a giant number. Now, here's what's really interesting is, Avogadro was an Italian scientist who's really most famous for his work with gases, proposing that different gases in the same volume at the same temperature and pressure contain the same number of particles. That's what he's most famous for, but it was his work that led to the idea, and later scientists coming in, the French scientist Jean Perrin, came in and used Brownian motion of particles to prove Avogadro's number. Around that same time, an American physicist, Robert Millikan, came in and did his famous oil drop experiment, where he was able to basically take the charge of a mole, which had been known for some time. You actually calculated it in a previous podcast of Faraday's constant, and to find the charge of an individual atom and divide the mole charge by the atom. And guess what number Robert Millikan came up with? Avogadro's number. Okay? So to help you conceptualize just how mind-boggling, massive this number is, I came across some images that really stood out to me, and that is a mole of sodium chloride placed right outside of Miami, Florida. Look at this. That is 1 mole of sodium chloride. This stands 27 miles tall, which is just unbelievable. And here, look at this, 280 miles away, outside of Tampa, looking back down toward Miami, almost 4 hours drive away. And you see how massive this mole of sodium chloride is. Now, to give you an idea of how small the atoms are, a mole of atoms would fit into the palm of your hand. Okay? All right, so we're going to be using a method in this course known as dimensional analysis, or the factor label method. Okay, your professors in college may refer to it as one or the other, but you will be using it. I typically just call it dimensional analysis, but it's a problem-solving technique of manipulating units of values until you get the units that are in your desired answer. All right, so I'm going to go through an example to kind of make a point here. And so our example is asking how many decades are equal to 1.7 times 10 to the 25th minutes. Now, I'm already starting to think and pay attention to sig figs and some things here. I have one piece of information, 1.7 times 10 to the 25th minutes, okay? I will typically put that over 1. Now, the way this works is I don't want minutes. I want decades. So I want to factor label my way and convert minutes into decades, all right? And in order to do this, I'm going to need to place minutes in the denominator here so it cancels out, all right? So there are 60 minutes in 1 hour. And then what's good is to go ahead and cancel, all right? And then we keep moving. Well, I don't want hours, I want decades. So then we can look at the fact that there are 24 hours in 1 day. Okay? Then we can say, I need to cancel days. So I have days in the numerator. I need to make sure day is down in the denominator. And so you can say, well, there's 7 days in 1 week. You see where this is going? And I don't want weeks, I want decades. And so there are 52 weeks in 1 year. Cancel, cancel. And I have years here. I need to get years on the bottom. And so I know there are 10 years in 1 decade. Cancel, cancel. equals. Now here's how this works. You will multiply everything in the numerator across. Everything on top, multiply it. Then you're going to divide by everything on the bottom. And there's a number of ways that you can do this with your calculator that you feel comfortable with. We have some scientific notation here. All of these other numbers are what we call exact numbers. There's exactly 60 minutes in 1 hour. They have infinite sig figs, so we want our final answer to have 2 sig figs, essentially. All right? So when you go through and you multiply all this out, you're going to get 3.2 times 10 to the 18th decades. Oh, spelling is not my strong suit, as you know. Okay, so 3.2 times 10 to the 18th decades, and that's your answer. And again, we wanted decades. We ended with decades. We used the factor labeling, i.e. dimensional analysis, to ensure our units were canceling. Here we end with decades, which means we're going to stop, and we're going to go ahead and pop this in the calculator. Bam, there we go. Okay, now, I've probably already given you the mole map, and we're going to be using this over the next several podcasts. So I'm just saying, you know, it's time to start thinking about the land of the mole a little bit. And I'm going to teach you how to use this so it makes sense. But in the end, you're going to find you don't even need a map for this land. Let's go ahead and do another example, a real chemistry example here. So how many oxygen atoms are in 3.2 moles of oxygen atoms? Okay, so what are we given? 3.2 moles of oxygen. What do we want? Atoms. Okay, so put this over 1 times. Okay, so I have moles on top here. I want moles in bottom, so I'm just going to write mole. And the connection, even if you're not, if it's not readily apparent, you know that we must end with atoms. If you see words, atoms, particles, molecules, you know you're using Avogadro's number. Okay, so the connection is, oh, in 1 mole, there are 6.022 times 10 to the 23 atoms. I want atoms in the end. My moles cancel. Okay? So when you pop this in, you're going to get 1.927 times 10 to the 23rd. But we're going to now pay attention to sig figs. So we're going to use 2 sig figs here. And so we're going to say final answer 1.9 times 10 to the 23rd atoms. Don't forget to include everything, atoms of oxygen. And that's going to be our final answer there. Okay. Another example. This is very cool. I like to throw this in from time to time. But so chromium ions are responsible for the color that we see in rubies and emeralds. It's really cool chemistry. If you look it up online, it's very interesting. So this question is saying how many chromium ions. So how many ions? I'm going to be using Avogadro's number. Are there in 3.5 moles? All right. See ya. Okay, so we have that many moles. That's how I'm going to start. Times. All right, so I need moles to be on bottom. And I specifically need the moles of the chromium ion on bottom. And even if you need to pause for a minute. Oh, wait a minute. This is Avogadro's number. In 1 mole of chromium ions, there are 6.022 times 10 to the 23 ions. Cancels, cancels. Okay, so ultimately we're going to get 2 sig figs on this. We're going to have 2.1 times 10 to the 24th ions of chromium 3 plus. Okay, so that's the basis behind dimensional analysis. We're going to get ready to get into some fun stuff here coming up. But now you have an idea. I hope I've provided a foundation for understanding a little bit more about atomic theory, but most importantly, this concept of the mole, because we're going to be applying these throughout the next several podcasts to do a number of computations. Now, we're getting close to being able to work on a problem set as well. I think we're going to go ahead and plan on looking at mole 4 next before I ask you to attempt these problems. So I will see you in class. Thank you.